Good afternoon, students. Welcome to the 26th lecture of Unit 3, that is refrigeration and air conditioning subject. Today in this class, we'll discuss about the classification of evaporators and the factors affecting the evaporators, and also the applications of evaporators in the compression variable refrigeration and absorption variable refrigeration. Right? Yes. So in the last class we have stopped the class here. As I said, what is the meaning of evaporator? An evaporator is simply a heat exchanger which is passing the heat from one device to the other device. From one device to the other device. Right? In the evaporator, the refrigerant, what we have studied in the last classes, the refrigerant boils or evaporates, and doing so it absorbs the heat from the substance being refrigerated. So what happens in the evaporator? Because evaporator is a heat exchanger, what happens, the refrigerant అనేది will get boils in the evaporator, thereby the substance being refrigerated. The name the evaporator refers to the evaporation process occurring in the heat exchanger. The name evaporator has come because of the evaporation process that occurs in the heat exchanger. That is the meaning of evaporator. Got it? So an evaporator is a substance or a device which is a member of the refrigeration system. It may be a domestic refrigerators or it may be the commercial refrigerators. Next, coming to the types of evaporators, right? So based upon the type of refrigeration system, that is vapor compression refrigeration system or absorption type of refrigeration system. So we are choosing various types of evaporator systems. So coming to the classification of evaporators, so the various classifications are derived as according to the type of construction, according to the physical type of construction. We are having 6 types of construction. One is the bare tube coil evaporator, bare tube coil evaporator, finned tube evaporator. Second one is finned tube evaporator. Third one is plate evaporator. Third one is plate evaporator. Fourth one is shell and tube evaporator. Okay. Fourth one is shell and tube evaporator. Fifth one is shell and coil evaporator. Shell and tube evaporator. Shell and coil evaporator. Sixth one is tube in tube evaporator. So like this, these are the 6 types of evaporators where you are having in the first according to the type of construction. Next is the second point is according to the manner in which the liquid refrigerant is fed. According to the manner in which the liquid refrigerant is fed. First type is flooded evaporator. First one is a flooded evaporator. Second one is dry expansion evaporator. First one is a flooded evaporator. Second one is dry expansion evaporator. Third one, according to the mode of heat transfer. So according to the mode of heat transfer, natural convection evaporator. Natural convection evaporator. Second one is forced convection evaporator. Third one is first one is a natural convection evaporator. Fourth one is forced convection evaporator. Next, according to the operating conditions, according to the what type of operating you are doing, according to the mode of operating conditions, first one is a frosting evaporator, second one is a non-frosting evaporators, third one is a defrosting evaporators. So like this, you are having 3 types of evaporators where the classification of refrigeration system you are having. Got it? Next, We'll see each of this classification in detail according to syllabus what you are having. Next, coming to the heat transfer in the evaporator. How the heat transfer is done in the evaporator? Being evaporator is a heat exchanger. Evaporator is a heat exchanger. How the heat transfer is taken place? First one, the resistance of medium being cooled. The heat transfer in the evaporator has the following three resistances in this path. First one is the resistance of medium being cooled. So the resistance, what type of refrigerant you are using, the medium being cooled, it's maybe the air, a water, brine, or any other fluid, or a wetted surface of a cooling and dehumidifying coil. Second one, the resistance of metallic wall tube or liquid. The resistance of metallic wall of tube liquid. Okay, so that is a second thing. The resistance of metallic wall tube liquid. Third one, the resistance of cool medium, that is refrigerant film, which gets heat from solid metallic walls. Okay, the resistance of cooling medium. What is the resistance of cooling medium? The resistance of cooling medium, that is refrigerant film, which gets heat from the solid metallic walls. That is a third type of heat transfer. Next. Next one is, what are the factors affecting the heat transfer capacity of an evaporator? Okay, so what are the factors affecting the heat transfer capacity of an evaporator? Though there are many factors upon which the heat transfer capacity of an operator depends, the following important are the subject point of view. So there are evaporator definitely generally there are various types of factors influencing the capacity of the evaporator, but these are the some of the important thing which will subject to the point of view. The first one is material. What type of material you are using for the evaporator? Right, material. In order to have a rapid heat transfer in evaporator, the material used for the construction of evaporator coil should be good conductor of heat. So heat transfer in evaporator is the main topic what we are discussing. So in the heat transfer, moving from one uh, place to other position, so first thing you have to see is the material. What type of material you are choosing for the evaporator? Why? Because the heat transfer should be done. Why? Because we are having a sudden heat transfer and the material should be good conductor of the heat. Next one. The material which is not affected by the refrigerant must be selected. So second one is the refrigerant material what you are using should not affect the material. For example, if you are using steel water bottle and you are pouring water, and if you are using copper and if you are using copper bottle, which one gives good thing? So in the same way here, we are the material which is not affected, the material which is not affected by the refrigerant must be selected. Third important point, since the metals are best conductors of heat, therefore they are always used for evaporators. So generally the metals are good conductors of heat. Any material which is having good rigidity is used for evaporators. Next one, iron and steel can be used with all common refrigerants. Brass and copper are used with all refrigerant except ammonia. Aluminium should be used with freon. Aluminum should not be used with freon. So these are the important points regarding to the type of material you are using, type of material you are choosing, the type of material you are giving for refrigerant, and the type of the refrigerant material. Second one, temperature difference. And the second factor is temperature difference. The temperature difference between the refrigerant within the evaporator Okay, the temperature difference. So refrigerant ki one type of temperature you are having, for the evaporator you are having one type of temperature, the refrigerant, and the inner wall of the evaporator should be of same thing. Okay, the temperature difference between the refrigerant within the evaporator and the product to be cooled plays an important role in the heat transfer capacity of an evaporator. The following table gives the temperature difference of for some products to be cooled. So what is the temperature difference saying? So it says that transfer capacity of an evaporator will be done by the refrigerant or what the material is chosen. Next. Next one is the table where it suggested the temperature differences for some of the products. See here, for the product cheese, eggs and butter. For the product cheese, eggs and butter. So for these products, what is the cooling temperature you should require? 0 to -2 degrees centigrade. What is the refrigerant temperature? -10 degrees centigrade. What is the temperature difference? 8 degrees centigrade. Next, for a poultry and meats which are frozen, -20 to 15. Coming to the resistance temperature. Next one, see the cooling temperature is -20 to -15 degrees centigrade. Coming to the refrigerant temperature, -30 degrees centigrade. And what is the difference you are having? You are having 20, 30 and about 10 degrees you are having. Next, coming to the vegetables and fruits. The cooling temperature what you are giving is 7 degrees centigrade. 7 degree centigrade. Next, for this, the refrigerant temperature is -5 degrees centigrade. Therefore, the temperature is 12 degrees centigrade. Coming to the next last one, cream, bed and milk. So the cream you are having is +3 degrees centigrade, -18 degrees centigrade. You are having 4.5 degrees centigrade. This is -7 degrees centigrade. Therefore, -7 minus 4.5, that is 11.5. So these are the material regarding to the things. Next, it may be noted that two low temperature differences, that is below 8 degrees centigrade, may call as slime or can certain products such as mint for poultry. On the other hand, too high a temperature and too high the temperature refrigerants and which gets right. So next one is velocity of refrigerants. Velocity of a refrigerant. The velocity of a refrigerant also affects the heat transfer capacity of an evaporator. So finally, the evaporators also makes a problem for this. The velocity of a refrigerant also make a problem for the evaporator. It is if the velocity of refrigerant flowing through the evaporator increases, the overall heat transfer coefficient also increases. But this increased velocity will cause greater pressure loss in the evaporator. Thus, the only recommended velocities for different refrigerants which give high heat transfer rates and allowable pressure loss should be used. Now see here, but if the velocity is increased, will cause greater pressure loss in the evaporator. The only recommended velocities for different refrigerants which give high rate transfer and allowable pressure loss should be used, right? So the pressure loss should be used whenever there is a different refrigerants which give high heat transfer rates, and allowable pressure loss should be used. So in this way also we can plan for this velocity of refrigerant. Okay, next, what is the next fourth point? The fourth point is thickness of the evaporator, right? Thickness of the evaporator coil wall. So the thickness of the evaporator coil wall. So for this, the thickness of the evaporator coil will also affects the e heat transfer capacity to the evaporator. Generally, the thicker the wall, the slower the rate of heat transfer. Obviously, whenever the wall is keep on increasing the thickness, the heat transfer rate will be very low. Whenever you are using a sheet plane or like that, the heat transfer flow is very fast, right? Since the refrigerant in the evaporator coil is under pressure, therefore the evaporator walls will be thick enough to withstand the collapse of the pressure, right? It may be noted that the thickness has only a slight effect on the total heat transfer capacity, because evaporators are usually made up of the high conductive materials. So that's why for this type of vehicles, if once the problem has started, so this will keep on starting and will never end up what is the real or wrong, right? Next, it may be noted that the thickness has only a slight effect on total heat transfer capacity, because the evaporators are usually made up of usually construction chips. So these are the some of the factors which will be facing, right? That's why it may be noted that the thickness has only a light effect with the total heat transfer capacity, because evaporators are usually made up of high conductive materials. So those are the thickness of evaporators coil wall information. Next, fifth one is contract surface area. Contract. Next one is okay. Next one is contact surface area. Next, fifth one is a contact surface area. See the figure here: wiped film evaporator with external condenser, short pan evaporator with internal condenser. So here the control surface area, how much surface should be controlled for the area to be done. An important factor affecting the evaporator capacity is the surface contact surface area available between the walls of the evaporator coil and the medium being cooled. The amount of contact surface in turn depends upon basically on the physical size and shape of the evaporator coil. So these are the things why the contact should be the on the surface area. Now see the wiped film evaporator with external features. So see the first point is a feeder. It is a feeder. It is automatically the out feeder vacuum. Now see the various parts of evaporator into different modules. See the first one. In the first one, the feed where you are dumping the material. What type of material? 3 weeks, right? So the material which are used for dumping is methyl or bucket, but it is a harmful. Okay. Now see the figure. The figure one shows the inlet feed. The figure 2 shows the distillation process. The figure 3 shows the drain process. Next, see the figure here. The feed, the distance, the residue, the heating, cooling, and vacuum. So where is the cooling here? At the point 5, that the point 5, the evaporator, it is having a cooler point, it is having a vacuum point, and heating point. 4 is a heating point. Next one. Coming to the short pan evaporator with internal condenser. See the internal condenser where it is located. So the feed is given at the bottom. The feed it is the one is feed one top and bottom. Next the distillate is shown in the option 2 downwards. Section option 3 residue heating cooling and vacuum. So these are the various techniques that are used for the casting are used for this process. Next, understood the figure? Next, if you see the capacity in an evaporator, capacity of an evaporator, coming to the capacity of an evaporator, the capacity of an evaporator is defined as the amount of heat absorbed it by it. So amount of evaporator is defined as an amount, the capacity of an evaporator be defined as the amount of heat shot absorbed by it over a given period of time. The heat absorbed or heat transferred capacity, the heat absorbed or heat transfer capacity of an evaporator should be given, right? Should be given. So if you see the Q is equals to U into A into UT minus 1 of T1 to W, right? Next, Q is equals to QA into T2 minus T1 W or joules per second. Therefore, capital U is equals to overall heat transfer of coefficient in W m square degree centigrade. Next, area of evaporator surface m square. Next, T2 is equals to temperature of medium to be cooled, that is last point. T is equals to T2 is equals to temperature of medium to be cooled. T1 is equal to saturation temperature of the refrigerant. Right. So these are the things to be happen for the capacity of an elevator. Coming to the main topic, there is a working of evaporator. So under the classification, we are having 6 various types of classification, but among all the 6 various types of AC refrigeration, you have to study how the evaporator works in the air conditioning system. Got it? See the points. The working of an evaporator may be understood by condensing the simple refrigeration system shown in the 11 point A. So what is this point saying? So the person is saying that the working of evaporator by effect the working of by working of an evaporator by working of an evaporator, it should be understood by the condition, it should be understood by the consideration of simple planning it, right? So first point, The corresponding pH diagram is shown in the figure. The point 5 in the final T represents the entry of liquid refrigerant into the expansion valve. Under the proper operating conditions, the liquid refrigerant is subcooled. See the figure now. See here. 11.1. This is a evaporator place. The liquid vapor mixture from the expansion valve, the liquid vapor mixture is going into the tubes and it is going to the evaporator. From the evaporator, it is going to the superheated vapor refrigerant, and later the water is going into the process. So we'll study this point. The right, the subcooling ensures that the expansion valves, the subcooling process ensures that the expansion valve receives pure liquid refrigerant with no vapor present to restrict the flow of refrigeration throughout the expansion valve. Right? Next, the liquid refrigerant at low pressure, the liquid refrigerant at low pressure enters the evaporator at the point 6, and from the figure shown 11, as the liquid refrigerant passes through the evaporator coil. See here, the liquid refrigerant at slope. Got it? Now, the subcooling ensures the expansion valves receives a purest form of liquid refrigerant with no vapor present to restrict the flow of refrigeration throughout the expansion valve. The liquid refrigerant at low pressure enters the evaporator at the point 6 as shown. As a liquid refrigerant passes through the evaporator coil, it is continuously absorbs the heat through the coin walls from the medium being cooled. During this process, the refrigerant continues to boil and evaporate. Finally, at the point 1 dash, all the liquid refrigerants have evaporated and only vapor refrigerant remains in the evaporator coil. So finally, what it is saying at the point 1, all the liquid refrigerant has evaporated and only proper refrigerant type you can fix it. Got it? Next, finally at the point 1 dash, the liquid refrigerant has evaporated and then vapor represent or what this the things what the liquid represent ability to convert the absorption heat to the latent heat is now used in this concept. So that is a simple concept of the working of an elevator. Now see the figure. So in this figure, since the vapor refrigerant at the point 1, this is a point 1 or this is a point 1. So since the refrigerant of at point 1 dash at a point 1 dash is still cooler than the medium being cooled, therefore the vapor refrigerant continues to absorb the heat. The heat absorption causes to increase in the sensible heat of a vapor refrigerant. The vapor temperature continues. The vapor temperature continues to rise until the vapor leaves the evaporator to the suction line at point 1. Therefore, as a point, the temperature of evaporator is above the saturation temperature of the vapor refrigerant is superheated. Got it? See here. 1, 2, right, in this compressor chamber. So 1, 2 through the tap and the pipe you can construct this elevator. From a 3 it is going to the condenser point where it is having the condensation process. Next one, liquid refrigerant. What is the meaning of liquid refrigerant? It is a form of medium which is used for boiling. Like this, the liquid refrigerant is passing from the 5 and is moving from the 3 and is going it and it is getting meshing process, right? So The vapor temperature continues to rise until the vapor leaves the evaporator to the suction line at the point. The point temperature of a refrigerator of a VCR. Got it? At the point 1, the temperature of the evaporator is above the saturation temperature and the vapor is superheated. So whenever it is above the point, automatically the vapor will get superheated. Now see the figure, the legend, the liquid vapor mixture inside, and it is passing to the evaporator for the vapor refrigeration. Again it is passing to the subcharged level. Okay, so later it is passing to the compressor and getting the information, and it is coming outside. Got it? If you see the graph of this one, the point 1 dash having many variation. The point from here, the 1 dash, it is a 1, right? Next, 2 to 3, 3 to 4, 4 to 5, 5 to 6. So if it is completed with the number of rows, and it is completed, so it is very easy to understand the concept of working of a evaporator. Next, now see the physical setup of the evaporator. It is aluminum evaporator. See the aluminum evaporator how it is. Okay. Now the figure 1.2 shows the variation of refrigeration temperature and the refrigerant heat content within the evaporator. We see that the temperature of refrigerant is constant during evaporation of the liquid refrigerant from the point 6 to 1 dash, and the enthalpy increases steadily. So both the temperatures and enthalpy of the refrigerant increases the point 1 and point A dash. All the liquid refrigerant has evaporated. The line 1 dash shows the increase in the sensible heat of vapor refrigerant. The sensible heat of vapor refrigerant. Now see the graph shows the graph on the x-axis it is enthalpy, and the P that is on the y-axis. Since the point from 1 to 1 dash, 1 dash to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to again 1. So the complete cycle completes, it gives the into this one. See here the process from here to 6 to 1 is evaporation process. Next, right. So on the x-axis you are having the enthalpy, and the y-axis you are having the pressure. You are having the pressure. See here, the point 1 dash, 2 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 5, 5 to 6. The first mistake then is the now see at the point 2 to 3 and 3 to 4. So the standard vapor line versus standard saturated liquid line. Saturated vapor line, saturated liquid line. From here it is going for the subcooling process. It is a reservoir, or it is an extension of the thing. It is a subcooling process. From subcooling process again it is passing to the exit point. So in this way the working of evaporator is done by using the refrigerants, oil, water, air, or brines. Understood? So this is the way of the working of evaporator does whenever it is right. So with this I will stop the class. I have the other class 220 to 3, and we'll continue the class in the tomorrow session. Mhm. To 1 second, 220, next. So with this we'll end the class. We'll discuss the topic tomorrow, working of a evaporator. See the evaporator, how it is, aluminum evaporator. So the entire setup from here to here. So the setup from here to here. So initially it has been mechanized. It has been a totally manual type, but now because of these electrical systems, it is some sort of electrical operation. Electrical operation. So it is aluminum operator where the string of aluminum sheets. Got it? And next point is okay. So we'll wind up the class. We'll discuss in the tomorrow's session.